Bismillahirrahmanirrahim. Assalamu alaikum. Today we will cover 1.1.2 probability. Let's look at the data from example 1.1 quite a little differently by creating a histogram of the data. We break the full range of the data into M segments known as bins. The bins have equal width and we label them as xj, j is equal to 1 to m. Note that there is no subscript m on xj because we are labeling x values corresponding to a bin, which is a value that could have been measured, not a particular measured value. We'll sort in visual measurement into bin, then count the number of measurements in each bin in xj. This process, known as histogramming, is best illustrated with an example. Example 1.2. Create a histogram of the data from example 1.1. The data values range from 5 to 25. Let's break this interval into 7 equal width bins. The first bin contains the measurement which yield x values of 5, 6, 7. And we'll label it bin x1 is equal to 6 corresponding to the center value. Bin x2 is equal to 9 contain values 8, 9, 10 and so on. Examining the data in equation 1.10, we find that one measurement yields a value of 5, 6 or 7. In example 1.1, we see that the measurement of x yields a value xmi is equal to 9, 5, 25, 23, 10, 22, 8, 8, 21 and 20. We notice that the range is from between 5 to 25. We will divide it into 7 equal bins. The first bin contains 5, 6 and 7 and only one measurement which is 5 that is included. In the second bin, which includes 8, 9 and 10, x2 is equal to 9. There are 4 measured values that exist, 2 8 values, 1 9 value and 1 10 value and so on. Examining the data in equation 1.1, we find the measurement yields a value of 5, 6 or 7. Thus the number of measurement in bin x1 is equal to 6, is n6 equal to 1. 4 of our measurements fall in the second bin holding values 8, 9, 10. So n9 is equal to 4. Continuing on this vein, we'll find the rest of histogram values. A plot of histogram is shown in figure 1.1. Let's study the histogram. We see that the range is from 5 to 25 and we have divided it into 7 bins, 1, 2, 3, 4, 5, 6, 7. And between 5, 6 and 7, we have taken the mean value which is 6. So n6 is equal to 1, n9 is equal to 4, n21 is equal to 3 and n24 is equal to 2. Histogram allow us to estimate the probability that we will obtain a particular measurement. The probability Pxj that a measurement will fall into a particular bin xj is simply the ratio of the number of measurement in that bin to the total number of measurement. In other words, Pxj is equal to nxj divided by n. Nxj is the number of measurements in a particular bin and n is the total number of measurements. The probability distribution corresponding to a histogram calculated in example 1.2 is plotted in figure 1.1. As can be seen, the probability distribution is a scaled version of the histogram. We can see from the histogram that x1 is equal to 6, x2 is equal to 9, x3 is equal to 12, x4 is equal to 15, x5 is equal to 18, x6 is equal to 21, and x7 is equal to 24. And if we see the probability, P6 is equal to 0.1, P9 is equal to 0.4, P21 is equal to 0.3, and P24 is equal to 0.2. Summing all the histogram values must yield the total number of measurement n. If the histogram has m bins, then j is equal to 1 to m, pxj is equal to j is equal to 1 to m of nxj divided by n. The sum of j is equal to 1 to m of nxj is equal to n, so n over n is equal to 1. Our probability is properly normalized, which means that the sum of probabilities is 1. If we look at the histogram again, N6 plus N9 plus N21 plus N24 is equal to 1 plus 4, which is 5, 5 plus 3, which is 8, 8 plus 2, which is 10, divided by the total number of measurements 10, so N over N is equal to 1. If we see the probabilities, P6 is P6 plus P9 plus P21 plus P24 is equal to zero point 0.1 plus zero point 0.4, which is 0.5, plus zero point 0.3, which is 0.8. 0.8 plus zero point 0.2 is 1. So the sum of the probabilities is 1, which means it is normalized. Equation 1.14 shows that Pxj is equal to Nxj over N. Equation 1.14 is only an estimate of the probability, and it's a fairly coarse estimate at that if the number of measurements n is small. Furthermore, with small n, it is necessary to use fairly wide bins, so the X resolution of Pxj is not very good. Conversely, if n is large, it is possible to obtain a fairly accurate and high resolution estimate of Pxj. This means that to obtain high resolution, large number of measurements should be taken. One thing we can do with probability distribution is simply plot it. This allows us to visualize our data and see which measured values are likely to occur and which are not very likely. For example, figure 1.1 tells us that measurement of x are clumped into regions, which is more information than simply saying that x is equal to 15.1 plus minus 7.3 from example 1.1. We can also use the probabilities to directly calculate moments without having to go back to the original data. Given the probabilities Pxj for j is equal to 1, 2 to m, the mean of x is given by the mean of x is equal to sum from j is equal to 1 to m xj times Pxj, which means that it is equal to x1 times Px1 plus x2 times Px2 and so on up till we keep on adding to x capital M times Pxm. Thus, to calculate the mean, weight the value by its probability and then sum over all possible values. In general, the mean of a function of x, f of x, is given by mean of f of x is equal to sum from j is equal to 1 to m f xj times Pxj, which means it is equal to fx1 times Px1 plus fx2 times Px2 and so on up till fxm times Pxm. Example 1.3. Calculate the mean and standard deviation of the data from example 1.1 using the corresponding probability distribution. Figure 1.1 shows the histogram of the data from example 1.1. We can use this histogram to calculate the probability distribution using equation 1.14. This probability distribution is plotted on the right axis of figure 1.1. Use these probabilities. Equation 1.16 tells us that we can get the values of the probabilities from the histogram. We see that P6 is equal to 0.1, P9 is equal to 0.4, P21 is equal to 0.3, and P24 is equal to 0.2. Equation 1.16 says that the mean of x is equal to sum from j is equal to 1 to m xj times pxj. In our case, the value of m is 7 since we have divided our data into 7 bins, which in the example that we are considering. So it would be x1 times px1 plus x2 times px2, so on up till x7 times px7. From the histogram, we can calculate the mean directly. We see that the mean of x is equal to 6 times 0.1 plus 9 times 0.4 plus 21.3 plus 24 times 0.2, and we get the answer 15.3, which is really close to the mean that we found in example 1.1. The equation 1.17 says that the mean of f of x is equal to sum from j is equal to 1 to m fxj times pxj, which means it is equal to fx1 times px1 plus fx2 times px2 and so on up till we'll keep on adding up till fxm times pxm. And equation 1.17 says that mean of x square is equal to 6 squares times 0.1 plus 9 square times 0.4 plus 21 square times 0.3 plus 24 square times 0.2, and this is equal to 283.5. The standard deviation is then delta x is equal to 283.5, which was the mean of x square, minus mean, which is 15.3, and we would square it. After we subtract this, we would take its under root and we would get the value of 7, which is the standard deviation. Note that the calculation of mean of x using the estimated probability distribution in example 1.3 is not in perfect agreement with the direct calculation in example 1.1, although the two determination of mean of x agree to well within one standard deviation. The agreement is not perfect because the probability distribution in example 1.3 is just an estimate of true distribution. In limit that the number of measurement is very large and the resolution of pxj is very fine, the estimated distribution will approach the true distribution and the mean calculated using the probabilities will approach mean determined directly from the data. This means that if we calculate the mean using the data, actual data, and if we calculate the mean using the histogram, there will be slight difference. But if the number of measurements that are being considered in the histogram are large enough, then it will be really close to the actual mean. Thank you for watching. Allah Hafiz.